First Spin. Welcome to First Spin, a show where I learn how to use the parallax propeller without having any prior programming experience. Rather than do this on my own, I have enlisted the help of two experts.
You keep calling me an expert on this show. I'm not an expert.
Well, you're more so than I am.
I'm very clever. I appreciate being
And
called an
humble.
expert, but I want to be clear. I don't do this professionally. Now, Roy, on the other hand, is a guru.
Hi, Roy.
Hi.
What's up?
I think Whisker is an expert compared to you. So
Yes.
Well,
It's
everybody's
okay.
an expert compared to Addie.
Burn!
Oh.
It hurts.
All right, where did we leave off last week, guys?
We had started talking about Brownout enabling and had talked about how if you have it low, then it is considered enabled and it helps to protect your circuit. Or your chip, actually, I should say. That's about right? Does that sound right, guys?
well, it protects the chip and the circuit
Okay.
by the
Chip-
actions.
Right.
And
chip
I
and the circuit.
was more along the lines of saying that it protects the person standing next to your giant robot.
Oh, that's right.
That too.
That's right. Okay. So it's generally a protection. It saves lives.
Mm-hmm.
Okay. So we'll continue with that if that's okay with everyone.
Sure.
Uh huh.
Okay. So it says here if low RESn becomes a weak output. So RESn, we haven't talked about that yet.
That's the next pin in the list, which is the reset pin.
Okay. So if low reset becomes a weak output for monitoring purposes, but can still be driven low to cause reset.
Right.
So that means if Brownout enabled, or if Brownout is enabled, then the reset pin becomes an output to monitor what?
To monitor the state of the brownout detection. So what happens is the reset pin is normally high, meaning you're not reset.
Okay.
And if you pull it low by connecting it to ground, it will reset the propeller. And the brownout pin, the brownout enable circuitry, when it's enabled, will drive the pin with a weak signal through a 5K ohm resistance to be high or low depending on what it has determined internally as the state. So it will be high normally, and if the power goes low, then it will pull the reset pin low with the 5K ohm pull down. And you could monitor that externally to determine, oh, the circuit got brownout detection. It might like set off an alarm or a light or something like that with a separate circuit.
And you connect that to the reset pin.
Right.
Okay.
And then, but the reset pin, what they're saying is that even though that is happening, the reset pin can still be driven low to cause a reset to occur.
So you can force it low.
Right. By connecting it directly to ground.
Now, do you normally put it high then?
Well, normally the reset pin will be pulled high by the brownout enable circuitry
Ah,
when there's no brownout.
okay.
Now, you could optionally pull it high yourself externally, but that would sort of get rid of the ability to monitor the state of the chip through it. Most people don't do that monitoring. It's just there as a feature so that if you have a more complicated setup that you want to monitor it and have some alarm go off or something, you can.
So do you remember last week how we were talking about how when the chip starts up, it checks to see if it's connected through the serial port pins, and if not, it downloads its program
From the eeprom?
from the eeprom through those pins.
Yep.
Okay? It does that when it resets. And you
Okay.
remember we mentioned that project that's out there where they have one prop giving the program to other props?
Yep.
In order to facilitate that main prop would obviously want to be connected to the reset pins on the slave props so that it can manually pull them down, reset them, and when they reset, they ask on their EEPROM port for their program.
Okay.
Make sense?
I think so. So I'm just going to double check here. Brownout enable is what monitors the system to see if the system goes less than 2.7 volts or whatever that threshold is for brownout.
Right.
Okay. And then when it's pulled low, then it also pulls.
Well, in order for brownout to be enabled, it is pulled low.
Oh, okay. So it's pulled low. And then, well, so if it's pulled low, then does the brownout do the monitoring or does the reset do the monitoring?
No, it allows you to have an external monitoring circuit connected to the reset pin, and it will drive the reset pin high or low with a weak output signal through a 5K ohm resistance. So it's basically pulling it high until a brownout occurs, and then it lets it go low. It sends it low.
High and then, okay.
And if you have something monitoring the reset pin, it will be able to read that pulling high or low from the brownout circuitry in order to work.
Okay, so that's like an extra perk.
Right. It turns the reset pin into an output as well as an input.
Okay, all right. Now, if BOE is high, if the brownout enable pin is high, set high, so in other words, not active, not enabled, then the reset is CMOS input with Schmidt trigger.
Right.
What's that mean?
So it's just a standard. The reset will be an input only and work like a CMOS Schmidt trigger for its input.
How do
So
those work? Or is that more electronics?
that's more electronic stuff, but it's basically the type of high or low signaling, detecting when it's high and when it's low kind of thing.
Okay. I think I actually did a little bit of research on this.
Yeah, that's definitely more
Before.
the electronic side of things and interfacing to it and whatnot.
Right.
And you do a lot of the electronics for your ham stuff.
Yeah.
But what you're lacking there is know-how when it comes to software. So
Yeah.
while these details are great to know, they're not necessarily serving your goals unless you run into some way to, at least keep track in your mind that that's there, because you could
Okay.
take advantage of it later to pull some really cool tricks. But for right now, your goals are much more heading towards the software side of things.
Okay. I have here some research though. And tell me if this is right or wrong. Okay. So if you disable brownout detection by setting the BOE high, then the reset pin goes back to its role as an input, where if it is high, if it's made high, the system stays where it's at normally. But if it's pulled low, the system resets.
Right. Well, it's always like that. The reset pin always works like that.
Okay.
But the
But instead
brownout,
of BOE controlling that, it's you controlling that.
well, you can always pull it high and low, regardless of the BOE, because like it said before, the output is a weak output when it's coming from the brownout circuitry.
Okay.
So you can override it by driving it low.
We
It will
talked a
pull
little
it
bit
high.
about this last week with pull-up resistors and pull-down resistors. Mm-hmm. Electrons take the path of least resistance. Mm-hmm. So if you're pulling it the opposite direction than what the resistor to the brownout pin is, then you can use a lower resistance than that, and you're going to win over. So
Okay.
like if you were to connect it directly to your 3.3, it would pull it high. If you were to pull it directly to ground, it would pull it low.
And it would reset the system.
Yep,
Right.
on the
Okay.
low.
And really all that matters for reset is that it's high when you're running normally and you pull it low to cause a reset to occur.
Okay. Okay, that makes sense. And actually, we can. That means we can finally. I will finally move us on to the reset pin.
And that's pretty much already been covered.
Right. So it says when low resets the propeller chip. Excellent. All cogs are disabled and IO pins floating, which means they go back to their default, whether pulled high, whether pulled low, and it doesn't.
Yeah.
Yeah. Okay.
It means that the propeller is not driving those pins.
Okay.
They will be driven by external sources, but not by the propeller.
Okay. And then the propeller restarts 50 milliseconds after the reset button transitions from low to high. Now, can I ask if, like, the fluctuations in the power line are such that, it'll all of a sudden go from low to high, low to high, to low to high? Like, what does that cause the system to do?
Well, the part of the reason that there's this little 50 millisecond delay before it will actually start up after you've reset is to stop that kind of thing. So if you had a noisy power for a second where the power went low and then high and then low and then high really fast, it would stay in reset because what would happen is the brownout circuit would go, oh, it's below the threshold, I'm going to pull us into reset mode. And then the power would go up and it would come back up, but 50 milliseconds won't have passed yet, and the power might go back down again because it's noisy.
So it's like resetting the timer every single time.
Right. Every
Okay.
single time it goes back between high and low, it's resetting, and it has to have 50 milliseconds of it being high before it actually starts doing anything.
Okay.
And that may seem like a very short time to us, but it's a really long time for the processor.
Well, I kind of remember something about like clock cycles from a couple weeks ago and how many like instructions can be.
So the propeller by default it will be able to run at 80 megahertz, which is 80 million cycles, right?
Yeah.
And each instruction, except for a few, takes 4 of those cycles to execute.
And there's,
So you
How
can-
many per second? So
and
how many
there's
per
8
second?
cogs going as well. Keep that in mind.
How many per second?
So 20 million.
And you'd say that as 20 MIPS.
Right.
20 million instructions per
Instructions.
second.
There you go.
And that's for one cog. And so you have 8 cogs.
So
you
50
take the-
seconds, 50 milliseconds is like an eternity.
Yeah,
kind
you can run quite a bit of program in 50 milliseconds. Yes.
MIPS. Ah, MIPS. What a cute little name for something so powerful. Okay,
Right.
so I'm okay with the reset pin, kind of beating a dead horse there, I guess, on my part. XI. It is an input. It is a crystal input. It can be connected to the output of the crystal or oscillator pack with the XO left disconnected, or to one leg of a crystal with XO connected to other leg of crystal. Depending on clock register settings, no external resistors or capacitors are required. So,
So, Addie,
yes.
when you're making schematics with the prop,
Yeah.
don't sign them with like XO, hearts, Addie, because that might get confusing.
That's just silly. That's just silly.
So what this is saying is you can use the XI pin either to hook up a oscillator pack, which only has one pin of output that will be a stable clock signal that you can connect to XI, and you don't have to bother connecting up the XO pin in that case. In the other case, where you're actually just using a regular crystal instead of an oscillator pack, then you would hook the crystal up to both XI and XO, the 2 pins of the crystal, and then that would allow it to operate.
So oscillator pack you only need to connect one pin. Crystal, you need to connect 2 pins.
Right.
Okay.
And that's because an oscillator pack has its own power and ground and enable pin, and then it has an output and an output pin, and the oscillator pack will produce a stable signal, a stable clock signal going up and down without needing to be driven. A
Gotcha.
crystal on its own won't really do anything. So they have the 2 pins allowing it to be fed back on itself and cause it to do its oscillations.
Okay.
And that's why you need the 2 pins.
Okay. And then XO is the crystal output, which we just referenced. Provides feedback for an external crystal or may be left disconnected depending on clock register settings. No external resistors or capacitors are required.
Right. So they're saying basically that that's where you would hook up a normal crystal to one of the pins of there and one of the pins to XI, like we just said. And you don't need any capacitors or resistors. Sometimes other processors do need external capacitors and resistors to help make the crystal circuit work. But the propeller doesn't need that.
Okay.
The other piece of the information there, depending on clock register settings,
Yeah.
the clock register is in the hub portion of the propeller, and you configure it with some commands that we'll get to later that tell it to use either the external clock, which is these pins, or to use an internal clock, which is less accurate but allows you to run the propeller without any crystal or oscillator. And that's
Right.
what they mean by depending on the clock register settings.
Okay, so you can program, or in the program you can dictate which clock you want, or which crystal or clock you want the chip to use.
Correct.
Okay, gotcha.
You can tell it to either use its internal clock or to use the external crystal. And you can do some modifiers on it too, to multiply
Multiply what?
multiply the clock signal. So like normally you don't have an 80 megahertz crystal. You'd have like a 5 megahertz crystal, and then you'd multiply it by 16 to get 80 megahertz.
And that's done internally in the chip.
Right. The
Okay.
chip has a PLL circuit internally that can do that.
What's a PLL circuit?
Phase lock loop circuit.
Okay.
And there's actually a really good video by Bill Hurd that goes into explaining how all that works.
Yeah, really good video.
You should go out and look for that one.
He's a Commodore guy.
Ah,
Right.
that's cool.
But basically, phase lock loops allow you to lock on to a signal and then optionally multiply that signal by multiples of powers of 2. So you can go by 2, by 4, by 8. And it lets you get a higher frequency signal from a lower frequency signal. It's a little more complex than that, but in this particular usage, that's what it's for.
Okay, so you say you have a 5 megahertz crystal,
Right.
and you want it to go up to 80 megahertz, which I think the system clock speed prefers, correct? Then you would multiply it with the PLL by 16.
Correct.
Okay, now can
And it doesn't prefer 80 megahertz. That's
Oh.
just the maximum that they certify the chip will
Okay.
work at. There are many people that run the propeller chip at much higher clock rates than that, but they do it without warranty from Parallax that it will work, because Parallax only guarantees that the chip will work at 80 megahertz.
Okay, up to 80 megahertz.
And in the
Right.
opposite direction, get all the way down to DC on
Correctly.
that pin, where you could actually maybe connect it to a switch and manually, bump it through each and individual clock.
Right.
Okay. Now, can I ask something about this phase locked loop? Can it change midstream, I guess? Like, so say you have the program running and you want the first however many instructions to run with a phase lock loop, multiplying the clock or the crystal by 16, and then for the next set of instructions you want it running at like PLL times, I don't know.
So you
Two.
you typically wouldn't do it at that granularity of like this many instructions or this one and then those many. You can change the setting of the clock register to change it to use different values, either different multipliers on the PLL or to use the internal clock versus the external clock. But typically you would do something like if you were going to go into low power state and put everything to sleep and just wait for some amount of time to pass or an external interrupt, then you could switch the clock to use the internal clock that's much slower, and it will cause the chip to use less power.
Okay. But
And
then,
that's like the typical usage. You don't want to be doing things like I'm going to run at 80 megahertz for the next 100 instructions and then turn it down to 40 megahertz for the next few and then turn it back up to 80. That's not a typical common usage. Part of the reason is that you actually have to delay a little bit after you switch it before the clock is stable.
sure.
So you'll switch the clock into one mode or the other, and then you have to wait usually half a second even, or maybe a little longer for it to stabilize on whatever clock frequency you chose.
Sure. Now, can you set like maybe each cog? Like, okay, so say you don't want to do the instructions, do it by instructions. Say you want to do it by cog. Could you do it by cog? So cog
The whole chip runs at whatever the clock register settings are at, because the clock register is in the hub, and the hub is a shared resource for all
see.
the cogs.
I see. Okay,
They're all running along in lockstep.
gotcha.
Because if you think about it, we're really talking about electricity under the hood. So when that clock goes high, it's feeding into the PLL. The PLL is interpolating where the beats are going to be in between, clock pulses. So if you're doing times 16, it's putting 16 beats for every, measure. Okay, so for each one of those, the chip is actually sending electricity through the circuit to those cogs.
Yeah.
And they get their electricity, and they electrically, through a bunch of transistors, do something.
Right.
And then the next beat comes along, and then that electricity goes through and flips a bunch of transistors around.
Sure.
Yeah, that's how what's really going on under the hood.
Sure.
So they are in lockstep electrically.
Now, is this the first thing that? So say I've got a crystal attached to, and let me accurately reference these pins to XI and XO.
Right.
Is that the first thing you want set in your program?
So there's actually special syntax in the spin or PASM document. When you make a project for your propeller, at the very top you put in a couple of lines of code that tell it what source you want and what multiplier, what frequency the external crystal is if you're using the external crystal. If you don't put those in, by default it uses the internal clock that runs at a much lower frequency.
So how would you write it? For the clock, for setting the clock.
Yeah, let me get to that. The exact syntax is always eluding me. I just copy and paste it for each program.
Well, that works.
Crap.
That's okay. And I know that we, on the demo board, which I've just started working on, it's got is it 5 megahertz crystal? And so I know there's like some XTAL and PLL, and I just wanted to clarify what those
So
were.
those lines in that program are doing exactly what Roy's talking about there. One of them is saying, the X, the crystal,
Yeah.
is a 5 megahertz crystal, and the PLL I want you to use is 16X.
Right. So the lines at the top are you have a clock mode, CLK mode. So it's underbar CLK mode and then equals. And then there'll be, for the case of using an external crystal, you put XTAL1, XTAL1. And then if you want it to be using the PLL multiplier, you would put plus PLL 16X for this case. You could put 8x or 4x or whatever,
Okay.
up to 16x.
Okay.
And then you have a line just below that called underbar x in FREQ for frequency,
Yeah.
and you tell it the frequency of the external crystal.
Which
in
is
this
5
case,
megahertz.
which is 5 million,
So
which
we
is
do.
how many cycles per second.
So you do it in hertz.
Right.
Okay. So let's look at this. So underscore CLK mode equals xtal1.
Right.
And xtal1 refers to the crystal.
Yeah, it's saying use the crystal.
Okay. Now, is this like, so say I bought a crystal and its name is Buddy. Do I put underscore clock mode equals Buddy?
No. You always use
awesome.
xtal1 because, well, there's actually 3 values that could be in there.
Okay.
xtal1, xtal2, and xtal3.
Okay.
And you're basically choosing the internal resistance and capacitance that it uses with the XO and XI pins.
Oh.
And by default, you use the xtal1 for external crystals that are 4 megahertz to 16 megahertz.
4 megahertz. That's so cool. Okay. So they,
And then if
Okay.
you used xtal2,
yeah.
then it's using a different setting for the resistance on the XO pin and the capacitance between XI and XO to allow it to work with a medium speed crystal between 8 megahertz and 32 megahertz.
Okay.
And then if you use xtal3, it uses yet still another setting that works with a high speed crystal that can be 20 megahertz to 80 megahertz.
Cool. So then, like,
And this
The-
is the difference between clever, me, and guru, Roy.
So the other values that you could possibly put in there are what they call RCFast or RCSlow,
Okay.
and those are to use the internal clock oscillator. And the fast one runs at approximately 20 megahertz, but it's really not stable and accurate, so it can vary between 8 megahertz and 20 megahertz.
well, that's a lot, isn't it?
Right, but it's okay for a lot of programs that just need to get up and running, right?
So, okay, I have a question then. So, say you use your internal clock, right? Now,
Right.
say it's running at 10 megahertz. Is it going to drift? Like, while it's running? Is that the risk that you run with not using a crystal? So, it may,
Yes,
with these, run
yeah,
at 8 and
it's
then...
it's all based on the power going into the processor and what all is going on with your signals coming out of the processor and stuff like that. It can drift a little bit up and down while you're going. Yes.
Okay. So
And
then...
okay, go ahead.
Okay. So I get the PLL 16X because you can change that. You can even take it away if you don't want to use the PLL. Like say you have an
Okay.
80 megahertz crystal, right? And then unless you want to overclock it, and
Yeah.
that's a whole different thing.
So just to clarify one other thing, the PLL values, there's only 5 valid values, and they're 1, 2, 4, 8, or 16.
Okay.
And it has to do with how PLLs work. They're only going to give you multiples of powers of 2.
Got it. Okay. And then I think the last thing we actually have time to cover.
We have no time. That's all
Well,
the time
I'm
we have.
almost done. The underscore X in frequency.
Oh, that's pretty simple. That's just the in hertz, the frequency of the crystal.
And X is referring to the crystal.
Right. It's just saying your X in, meaning the crystal input.
Oh, I see. Frequency. Okay.
All right. Did we sufficiently
Brilliant.
answer the questions you had for this week?
Yes. Actually,
Excellent.
and we did a great job going through the pin descriptions. Thank you guys for your patience.
Well, we will be back next week with more, but for now, we're going to get out of here. You can find this show every week on Tuesday at firstspin.tv, and we'd like to thank Ken Gracie and Parallax for sponsoring the show. We very much appreciate it.
Yep.
It makes this a lot easier to do, and we'd like to do a lot more. So thank you guys out there.
All right. See you guys next week.
Bye.
Take care.
Bye.